So thank you for the nice introduction, and it's really a pleasure to be here in San Francisco. The first time for me to be here, beautiful city, although I didn't have the chance to see downtown a lot, but on Sunday I had a chance to travel with the nice, let's say, tram system here. And when I watched all the presentations in the last couple of days here, I noticed that many of you talk about molecules and how they interact with protein systems or biological systems. Sometimes these molecules are also synthesized in your presentations. But actually that last part, that's the focus of the research that I'm doing in Amsterdam with my group. So we are organic chemists, synthetic organic chemists, and actually we turn the whole thing around. We just make the molecules and see if we can let them interact with all kinds of biological systems. So if I show you this slide, you see here a graph which involves the CO2 emission data, which is correlated with, let's say, life expectancy. And then you see that if you produce more CO2 as a country, your life expectancy is much higher. I thought it's a nice draft because it would set the whole discussion around this problem on a different light. And we, and probably you, more than even myself, like to think that this growth or increase in life expectancy actually comes because we are really able to make good medicines, good drugs that can help us in the treatment of a lot of diseases. But actually, this might also come because when you produce these drugs, they really produce also a lot of CO2. Because if you look at waste production, the pharmaceutical industry is actually one of the industries that produces most, let's say, kilogram of waste per kilogram of product. And of course, this is just a little bit of teasing you, but really it's a problem if you look at these figures. In pharmaceutical and specialty chemicals, the E factor, which is a factor that describes the amount of waste produced per kilogram of the product that you make, is really much higher than, for instance, in the, well, dirty petrochemical industry. So what can we do about this? I mean, we need actually methodology that helps us from the start to avoid this. Just one other slide to demonstrate that this really is a big problem. This is the structure of sildenafil. Many of you, or some of you, might know it as Viagra. And when this came from the medicinal chemistry labs, almost 2,000 liters of waste were produced per kilogram of sildenafil. And fairly quickly, but still it took quite some time, to the now commercial route, which produces still 10 liters of waste per kilogram of sildenafil, but is quite efficient. So what, this would of course be much more efficient if we would start thinking about efficient methodology to make molecules right from the start. So already in this phase. And that's actually what we are doing in my group. We focus on synthetic method development, and we try to develop methodology which is simple and based on one-pot processes, so-called multicomponent reactions. And then we apply this methodology to make complex molecules, and we try to address some issues in this chemistry around asymmetric induction and biocatalysis. And these are just a number of molecules and products that we are working on. And today I will talk a little bit on a project on this molecule here. And I will talk also on a project that is not on this slide actually, but is a very recent work, which is a new carbonylative, or actually imidorelative isocyanide insertion reaction. So these one-pot processes, we believe, would be really great if you start thinking about these right from the start when you design a molecule and start making it. So for the first example that I would like to discuss with you, I would like to first draw your attention to a multi-component reaction, the so-called UGI four-component reaction. And that's a reaction where you in one pot can produce amides or bisamides, which are useful compounds also in pharmaceutical industry. Many products are made by the UGI reaction. And that combines, in fact, an amine, an aldehyde, a carboxylic acid, and an isocyanide. These reactions are, although they are very efficient, are very poorly regarding their diastereoselectivity. So you produce here a stereocenter. So the enantio and diastereoselectivity, if you have other centers there, is very low. If you look at the mechanism of this reaction, you first have a condensation to the imine of the aldehyde and the amine. This is then activated by the carboxylic acid. The proton activates the imine. You form an iminium ion. And then the isocyanide attacks on the carbon here. You form this intermediate. And then the carboxylate attacks on the deuterium ion. You get a rearrangement reaction, and then you form the amide. So already in the first, let's say, steps of the synthesis, you form the chiral center. So until now, there's no stereoselective catalytic way of doing this reaction, and still people are really looking for it, including ourselves. An approach that we took to sort of deviate or overcome this problem was using enzymes to catalyze this reaction. And we did this in collaboration with Nick Turner from the University of Manchester, who is an expert in biocatalysis. And he had an enzyme, this monoamine oxidase, and he was able, by directed evolution, to, let's say, transform the wild type enzyme into an enzyme that could accept a broad range of different types of substrates that can make these chiral amines. And how could these then work for our UGI reaction, you might wonder? So we thought if we would use these type of cyclic, symmetric, secondary mesoamines and let them react with monoamine oxidase, you would in fact desymmetrize and get a chiral imine. Well, this chiral imine would then be an input for an UGI reaction, and if this would occur diastereoselectively, you would get to this type of UGI products in a stereoselective fashion. So we did a lot of optimizations, and we found indeed that this works. So if you have this type of imines produced by the MAO-N reaction, do the UGI reaction, as you see, you have nice selectivities, diastereoselectivities, and also your scope is quite good. We proved the stereochemistry, and as you see, it's always the RSS configuration. And you can also vary in the imine, and in the meantime, we can use different types, a whole range of different types of cyclic mesoamines, in fact, for this reaction. So now for the application, what is it good for? So we came in the literature across this molecule, telaprevir. It's a drug which is currently on the market, but at the time that we were starting this work, it was not yet on the market. It's quite a complex amide, and it's a medicine against hepatitis C, which is quite an important disease all over the world, as you see here on this graph. And the synthesis which is reported and which is also actually used in, by industry to make the molecule is a 24-step total synthesis with an overall yield of around 6%. So we thought we might do better if we use our methodology, our multi-component strategy and biocatalysis involved. If you do a retrosynthetic analysis of this structure, you can, let's say, split it up in three more simple units, this carboxylic acid here, this mesoimine, and this very typical complex-looking isocyanide. This one is already reported. We could easily make this molecule as well, and this one we can make from our monoamine oxidase reaction, and this one we thought we could make from this chiral amino alcohol from the chiral pool effect and use another multi-component reaction. This is a Passerini type reaction. So we would then use two multi-component reactions and one biocatalytic step. So indeed, this turned out quite useful. Maybe the greatest challenge in our synthesis was making this peculiar isocyanide here, but also that went pretty efficient. If you start from this chiral pool material, making the formamide, and then with an Des-Martin periodinane oxidation, transform the alcohol to an aldehyde. Then you do the Passerini reaction with this very smelly isocyanide, I must confess. This acetic acid, you form the Passerini product. The diastereomeric ratio is not great, but in the final step of the synthesis, you will destroy this stereocenter anyway, so it's not really important. We also figured that if you would do the Des-Martin periodinane reaction and the Passerini reaction in one step, you might skip one step, because the Des-Martin periodinane as a waste product actually produces acetic acid which can be used in this step. And indeed, that works, and the yield is even better. So in 3 steps, we can do in pretty good yield this rather complex building block. So then, we indeed did the monoamine oxidase reaction, do the Ugi type reaction with our advanced isocyanide, get to the coupled product, and then hydrolysis here and oxidation gives us telaprevir. And this is really a very useful method if you compare our route to the route that's currently used. We have a route which is only 7 steps, with which 45% overall yield, and in the meantime we have produced with our methodology more than 100 kilogram of telaprevir. So I hope this shows that if you think cleverly about synthetic sequences using one-step approaches, you really can go and have a lot of advantages. So then I would like to shift to another project which is completely different than this one, but also involving one-step chemistry, and that actually takes advantage of catalysis, carbonylative cross-coupling reactions. Probably many people of you know that. Recently, even the Nobel Prizes were awarded for that. And this is, in fact, the typical scheme. You have carbon monoxide, a palladium catalyst, and then you get to these type of structures. We thought, if you look at the isocyanides, they might be isoelectronic with carbon monoxide and then give you some additional advantages. I mean, you don't have to use with a gas, so you can do homogeneous conditions. You can use stoichiometric amounts of the isocyanide. You have even an extra diversity point, so getting structural diversity in there. The only problem might be this multiple insertions providing or getting to polymeric materials. So in fact, this is then what the plan was. Instead of using carbon monoxide, use a isocyanide in the catalytic cycle and then end up with these type of products. So if you look in the literature, there is really not much known about this type of chemistry. There was a very nice paper in, let's say, the early 2000s, and then actually not so very long ago, we published a couple of papers in this area, and in the last couple of years, really many people use the methodology to make these type of let's say, privileged heterocyclic scaffolds. Here are just a couple of older examples from our group. What I would like to show you is the most recent work, and that focuses actually on this privileged, let's say, structural entity. These are just examples of molecules that are on the market or are already quite old, that are clinically in use or have been used with this so-called guanidine motif. And we thought, can we do this in one step by using this type of starting materials, isocyanides, and then with palladium-2 catalysis under oxidative conditions. So I will not bore you with the optimization. I could probably fill a complete lecture with only this work here, but I can tell you that we managed to indeed find really good conditions to do this reaction with palladium acetate in an oxygen atmosphere of 1 atmosphere, and you get really good yields of the guanidine molecule. It's really general reaction, because here you see what we have been able to make. You can vary in the aromatic part of the ring. You see here a lot of different types, but also you can vary on this position here on the nitrogen. You can do heterocyclic rings. You can do this type of guanidines, and even these molecules are working. You might wonder, why is there always this tertiary butyl group? Well, that's because this is actually the group that works best in our chemistry. It's very easily removed, because you can do a one-pot process by combining the oxidative coupling with the dealkylation strategy, providing you the free guanidine here. So a couple of, let's say, applications. Here you see an antiviral compound which is on the market, which is also used against inflammatory diseases and as an anti-obesity drug. And we thought we could make this perhaps by our carbonylative cross-coupling reaction. So after some modifications of the initial circumstances, we were able to indeed get in very high yields a whole range of different structures of this type, which in principle could all be used. So I got the notice of the chairman that I have only a couple of minutes left, but I am also nearly finished actually. This is just another example where this chemistry can be used to get to compounds that are really of use. So in this case, we could even vary the isocyanide functionality here. So this part of the molecule can also be varied by using different isocyanides. And then you see that you also can get different type of scaffolds here. So I hope that I've shown you in the last 20 minutes that our chemistry is actually quite versatile. This is some slides of people that have already are using our chemistry in their own work. But I hope I've shown you that in the two projects that I've presented, you can combine multi-component strategies with biocatalysis in order to get fast complexity generation and introduction of chirality. And on the other hand, that you also can use clever carbonylative strategies, palladium catalysis, in order to make a whole bunch of privileged heterocyclic scaffolds that are of medicinal use, and that this methodology, in both cases, actually, you can consider as relatively green compared to many of the standard methods that are used. These are the people in my group, and especially highlight the people that worked on the projects that I have shown. Anna Snabet on the biocatalysis, and Gitte van Baalen and Justel Sla on the isocyanide insertion reaction. And these are our funding agencies, and thank you for your attention.
Floor for one more question, perhaps? Yeah. Since I skipped you last time.
Very nice work. I really enjoyed it. So on what did you make all these kilograms of Cinderfil for? Or did you just actually, did a company use your method to make these large quantities? I mean, I'm just anxious to know, you know, whether on the scale-up process, did you try to organize the scale-up, or did you have to go to a company to do it?
So for the teleprovir, you mean?
Yeah.
So yeah, we patented our procedures in 2 patents, and we licensed our method, and a generics company is actually using our method to make the material now, and they have produced this.
I believe this compound is still under patent, though. So what does this generic company do with all of
well,
this?
Well, they expect that in due course it will be off patent, and some countries you can still bring it on the market.
Okay, we have a very, very quick question.
Yes, from a technological point of view, have you imagined to use thermostable enzyme to be able to make the reaction at higher temperature, or modify enzyme to make them more stable in organic solutions?
Sorry, a thermostable enzyme for
yes,
which
because the enzyme you use here was used at room temperature, and usually you are using your reaction in chemistry are done at high temperature or in organic solvent. So I wonder if you may use this thermostable enzyme, like in PCR, for example.
We have not considered it ourselves, but in this particular case, so the UGI reaction is usually done under room temperature. Actually, if you heat it up, it gets worse. So the efficiency of the UGI reaction is better at room temperature, or even a little bit lower. But in principle, you could use thermostable enzymes as well for other types of transformations. So yes.
Okay, with that, let's thank Professor Orru again for a great talk.